Good morning, everyone. Today you are going to solve some questions related to Chapter 2 in Molecular Physics. This chapter was mainly discussing purely rotational spectra. So let's start. Before starting, I have printed the constants that we are going to use throughout our solution. Na represents the Avogadro's number, H is Planck's constant, Kb is the Boltzmann constant, C is the speed of light in vacuum, and mu is the atomic mass unit. Let's start with this exercise. Consider the CO molecule where we have two isotopes of the atom C, 12C and 13C. The transition from J equals 0 to J equals 1 happens at 3.84235 cm minus 1 for C12O and at 3.67337 cm minus 1 for C13O. The first part asks to find the rotational constants of C12O and C13O. So let's start. Let's first check the given. We have two important given, the transition from G equal 0 to G equal 1 for C12O and the transition from G equals 0 to G equals 1 for C13O. We have to make benefit of this. So because he's giving me the transitions as wave numbers and I already know the formula, so let's say this is part A, the wave numbers of the allowed absorptions from J to J plus 1 are given by U bar from J to J plus 1. They are equal to 2 B bar J plus 1. We have already showed that in the course. So if we are talking about a transition from J0 to J1, that means in U bar from 0 to 1, we have only to substitute 0 for J, we get 2 B bar 1, so it's 2 B bar. In reality, the number given here represents the wave number of the absorbed photon for a transition from a level of J equals 0 to J equals 1 for the molecule C12O. And this number here is the same, it is the wave number of the absorbed photon for a transition from the level J equals 0 to J equals 1 for the molecule C13O. So these two values are equal to 2 B bar. So if we know them, we are able to find B bar for C12O and B bar for C13O. So let's do that. So B bar for C12O is simply equal to nu bar for a transition from 0 to 1 over 2. It's equal to 3.84235 over, I'll keep it in centimeter minus 1. So to get the final answer in centimeter minus 1, this will give me 1.921175 centimeter minus 1. Same for C13O. So it's equal to nu bar over 2, nu bar for a transition from J equals 0 to J equals 1, and it's equal to 3.67337 over 2, which is equal to 1.836685 centimeter minus 1. And this is part A. Part B says, determine the mass of the isotope C13. To find the mass of the isotope C13, he gave us the mass of C12 and the mass of oxygen, and we have to make benefit of the part A for sure in order to find the mass of C13. The first thing I'm going to do is write the expression of the rotational constant V bar, the general expression of the rotational constant V bar. Let's do that. So This is part B. We know that the rotational constant has the formula. So in general, B bar is equal to H bar. H bar is H over 2 pi. So it's over 4 pi C. C is the speed of light in vacuum and I is the moment of inertia of the molecule. So it's H bar 4 pi C. Because we are dealing with a diatomic molecule, I is equal to mu R squared. So in both cases, for C12O and for C13O, R is the same because the internuclear distance does barely change with isotopes. So if we replace C12 by C13, the length or the internuclear distance, the length of the bond barely changes, and we have seen that in the slides when I've explained the lesson. So R will not change. What will change between these two molecules? The difference lies in mu. It lies in the reduced mass of the molecule. Because the mass of C13 is higher than the mass of C12, that's for sure mu for C13O is larger than mu for C12O. Now because we have B for C12O and B for C13O, let's calculate their ratio. So B for C12O over B for C13O, it's equal to 1.921175 divided by 1.836685. This is equal to 1.04600. Let's write the same ratio again, but replace B bar by its definition. So B bar for C12O divided by B bar for C13O is equal to H bar over 4 pi C mu for C12O R square for sure, all of it divided by H bar over 4 pi C mu for C13O times R squared. So as I have said, R is the same, H bar is the same, 4 pi C is the same, the only difference lies in mu. So this is equal to mu for C13O divided by mu for C12O. Mu is the reduced mass. So what's the definition of the reduced mass? The definition of the reduced mass is equal to the multiplication of the masses over the sum of the masses. For sure, if we are talking about a diatomic molecule. The reduced mass mu for C13O is equal to the mass of C13 multiplied by the mass of O, so this is times, over the mass of C13 plus the mass of O. Remember, the mass of O is given, we are searching for the mass of C13. So, the reduced mass, mu, which is for C12O, is equal to m C12 multiplied by the mass of O divided by the mass of C12 plus mass of O. We have a mass of C12, mass of O, we can substitute this, but I'm not going to substitute for it to keep the number as precise as possible. I will leave substitution till the end. So let's write the ratio in terms of masses. I'll go down. So now B bar for C12 O over B bar for C13O is equal to, we said it's mu C13O over mu C12O. So I will write M C13 multiplied by M of O divided by the mass of C13 plus MO, and multiplied, I will inverse the second one, so it's the mass of C12 plus, this is just mathematics, you can do it as you like, so it's M12C plus or times, I've inverted this one, times M. So we can get rid of MO from both sides. We know that the answer of this ratio, it's here, it's 1.046, so it's 1.046 equals to 1.046. We know everything, we know the mass of O, we know the mass of C12, we know the answer of the ratio, we have to find the mass of C13. Let's arrange the equation, so we will get implies mass of C13 multiplied by mass of C12 plus mass of O equals 1.046. We have a mass of C12 multiplied by mass of C13 plus MO, just cross multiply. So I'm going to arrange MC13 to one side, so we will get M mass of C13 into M mass of C12 plus mass of O. So here we have, it's multiplied by 1.046 mass of C12, so I get it to the other side, it's minus 1.046 mass of C12, so it's like this, and here there remains 1.046 mass of C12 multiplied by mass of O. So you can expand and then grab them to one side as you like. It's just mathematics, and I'm doing it as fast as I can. So now the mass of C13, I've kept substitution till the end to get precise numbers. Okay, it's equal to 1.046 mass of C12 times mass of O over 1 mass of C12 minus 1.06, I can get rid of 1, it will be MO minus 0.046 MC12, like this. So these are O's. Okay, this is equal to, let us substitute, equals 1.046 times mass of C12, it is 12 given, mass of O is given to be 15.9994 divided by mass of O is 15.9994 minus 0.046 times 12. So after calculating this number, we will get 13.000535 atomic mass unit. Mu is the atomic mass unit, or it can be written as AMU. Both of them are correct because you are trying to find the mass of one carbon atom. It's in Mu. Let's move to this question. The second question says, if the wave number of the rotational transition from a level j equals 2 to j equals 3 of HBr considered as a rigid rotor is 50.79 cm minus 1. So this is the wave number of transition. What is the moment of inertia of the molecule and the bond length? I'll try to use the given. He gave us the wave number of transition, which is equal to 50.79. Let's write the expression of the wave number of absorption. So the wave number of absorption in general, which is nu bar, for a transition from a level j to a level j plus 1 is equal to 2b bar j plus 1. So in our case, we have a transition from 2 to 3. So we will get nu bar equals to 2b bar. So this is 2 plus 1 equals 6b bar. So he gave us nu bar for a transition from 2 to 3, which is equal to 6b bar. So we are able to find b bar. Once we find b bar, we are able to find I, because the rotational constant is related to I. So now the rotational constant B is equal to nu bar for a transition from 2 to 3 divided by 6. It's equal to 50.79 centimeter minus 1 divided by 6. So it will be 8.465 centimeter minus 1. Now, we know the relation between B and I. B bar equals H bar over 4 pi Ci, where I is the moment of inertia of the molecule. So it can be written as H over 8 pi squared Ci, because H bar is equal to H over 2 pi. So remember, we are searching for I. I'll write it here. I equals H over 8 pi square C B bar. We have H, it's a constant, C is a constant. We have calculated B bar for our molecule, and now we are able to calculate I. So H is equal to 6.626 times 10 to the power minus 34, it's in joule second, over 8 pi square, 3 times 10 to the power 8, this is meter per second. So I have to change B bar to meter minus 1, or I can change C to centimeter per second. Anyway, I'll change B bar. It is 8.465 times 10 to the power 2 meter minus 1. So remember that if I want to change from centimeter minus 1 to meter minus 1, I have to multiply by 10 to the power 2. And in the opposite sense, from meter minus 1 to centimeter minus 1, I have to multiply by 10 to the power minus 2. The answer is 3.304558 times 10 to the power minus 47 kilogram meter square. This is the moment of inertia of the molecule. Now, in part B, he asks for the bond length. We have found I, we are able to find the bond length, which is R. So remember that I is equal to mu R squared, where mu is the reduced mass of the molecule. What is the reduced mass? It is equal to mH multiplied by the mass of Br divided by mH plus mbr. For sure, times R squared, which is the internuclear distance, or the distance between the two atoms. Now there are two methods to calculate mu. Either you substitute for the masses as masses of moles, and then you divide by Avogadro's number, or you divide directly by the masses as masses of atoms in a molecule, and you get your answer in atomic mass unit, and then you change to kilograms. If the masses of the atoms are not given, we can make benefit of mass number. It gives an approximate value of the mass of the atom. So for H, the mass of H, if I'm going to consider 1 mole of hydrogen atoms, it's equal to 1 gram per mole. So 1 mole of hydrogen atoms has a mass of 1 gram, and the mass of 1 mole of Br atoms is equal to 81 gram per mole. Remember, these numbers 1 and 81 are the atomic masses of H and Brs. So if I'm going to substitute this in the reduced mass, I will get 1 times 81 over 1 plus 81. The unit of this will be gram per mole. So I'm not searching for the reduced mass of a mole of molecules. I'm searching for the reduced mass of a single molecule in kilogram. So to change it from gram to kilogram first, I have to multiply by 10 to the power minus 3, because here the final answer will be in gram per mole. So I have to multiply by 10 to the power minus 3 to change it to kilogram, and then divide by Avogadro's number, which is 6.022 times 10 to the power 23, which is the number of molecules in a mole, mole minus 1. So at last, or in this case, mu will correspond to the reduced mass of a single molecule. Calculating this will give us 1.640 times 10 to the power minus 27 kilogram. So this is the reduced mass of a single molecule in kilogram. Now there's a second method. Instead of substituting the masses in gram per mole, or substituting the masses for a mole of molecules or mole of atoms, we're going to substitute the masses directly in their atomic mass units. So this is 1 mu, and mbr, it's equal to 81 mu. So in this case, there is no need to divide by Na, by Avogadro's number, because we're already calculating the mass of a single molecule. So it's equal to 1 times 81 divided by 1 plus 81. So this has a unit of mu. This is the mass. So to change it to kilogram, we have to multiply by 1.66054 times 10 to the power minus 27. So in this way, we get the same answer of above, 1.640 times 10 to the power minus 27 kilogram. So why did I multiply by this value? Because 1 mu is equal to 1.66054 times 10 to the power minus 27 kilogram. It's found up in the given constants. So now after finding mu, we have I. Now r squared equals I over mu implies R equals radical I over mu. I is already calculated, 3.304558. So take numbers as much as you can always. Minus 47 divided by 1.640 times 10 to the power minus 27. Everything is substituted in SI units. So this is kilogram meter square, and this is in kilograms. So we expect to get the distance in meter. It's found to be 1.419 times 10 to the power minus 10 meter. So it can be written in nanometer as 0.1419 nanometer. And if you like in picometer, it's 141.9 picometer. So remember that a transition from nanometer to meter, we multiply by 10 to the power minus 9, and the opposite direction is 10 to the power 9. And from picometer to meter, we multiply by 10 to the power minus 12, and in opposite direction, we multiply by 10 to the power 12. So that's it. This exercise says rotational absorption lines from H1Cl35 gas were found at the following wave numbers. The wave numbers are given in centimeter minus 1. So these numbers correspond to the wave numbers. So if we have a spectrum will have lines, okay? And the wave numbers are at 83.32, this one is at 104.13, etc. So in part A, he's asking for the moment of inertia and the bond length of the molecule. One important thing is that we know the spacing between the lines of a spectrum. The spacing is equal to 2b bar, 2 of the rotational constant. So if we are able to calculate b bar from the spectrum, then we are able to calculate the moment of inertia because b depends on I. And then if we calculate I, we can calculate the bond length of the molecule. So let's do that. I have calculated the difference between two consecutive lines and it turned out to be like this. So this is part A, the separation or the separations between two neighboring lines are, so between the first and the second it was found to be 20.81 for sure centimeter minus 1. Between the third and the second it was found to be 20.6 and then 20.64, 20.52, 20.34, 20.37, and the last one was 20.26. So what I have done is that I subtracted this from this to get the first one, then subtract this from this to get the second one, then this from this to get the third, this from this to get the fourth, this from this to get this one, until I finished all of them. So I was searching for the separations between two consecutive lines. For sure, this is in centimeter minus 1. You can see that all the values are approximately constant with an average 20.51 centimeter minus 1. So this is the average. Now we can say that B bar, hence B bar is equal to half this value because the distance between two consecutive lines is 2b bar. So B bar is equal to half 20.51 centimeter minus 1 and the answer will be 10.25 centimeter minus 1. Once we get B, we are able to calculate I. Remember that I equals h bar over 4 pi c b bar. It's equal to h over 8 pi squared c times b bar. We have everything. H is equal to 6.626 times 10 to the power minus 34 joule second. I'm going to substitute everything in SI unit. So over 8 pi squared, C is equal to 3 times 10 to the power 8, and B bar is 10.25. I'm going to change it to meter minus 1. So I'm going to multiply by 10 to the power 2, which will give me 2.729 times 10 to the power minus 47 kilogram meter square. So after finding I, we have to find R, the bond length or the internuclear distance. So we know that I equals mu R squared, where mu is the reduced mass, equals mass of H1 multiplied by mass of Cl35 divided by mass of H1 plus mass of Cl35 times R squared. So we have to find R squared, implies R squared for R, let's find R directly, equals, I'll substitute 4 numbers, it's radical I over mu, I over mu, it's equal to radical. I is already calculated. It's 2.729 times 10 to the power minus 47. The masses of H and Cl are given up in atomic mass unit. So I'm just going to use these values. 1.0078. This is the mass of H1 times 34.9688. This is the mass of Cl35 divided by same values but with a plus sign, 9688. Remember that the final answer of this mu is in atomic mass units, so to change it to kilogram, to get everything in SI unit, I have to multiply by 1.66054 times 10 to the power minus 27. In this way, my answer here is in kilogram, and up it is in kilogram meter square, and the radius will have a unit of meter. So the final answer will be 1.295 times 10 to the power minus 10 meter, which is equal to 129.5 picometer. And this is the answer. In the second part B, he's asking to predict the positions of the corresponding lines in H2Cl35. So he replaced the hydrogen by its isotope, the deuterium. What happens if we replace an atom by its isotope? In reality, the bond length barely varies, so we can consider that the bond length remains approximately the same. But what varies is mu, the reduced mass of the molecule. If mu varies, then I will vary, and if I varies, then B bar will vary. So the separation between the lines of the spectrum will vary. So let's predict these positions. We are able to calculate B bar for the molecule H2Cl35. We're able to do that. We have everything. We can calculate the moment of inertia of the molecule since we are able to calculate mu, the reduced mass. The masses are given, and R is approximately the same. So we are able to calculate B bar for H2Cl35. But I'm not going to do that. I'm going to do it in a simpler way. This is part B. I'm going to find the ratio of B bar for H2Cl35 to B bar H1Cl35. So this is equal to H bar over 4 pi C. Pi is equal to mu for H2Cl35 multiplied by R square, all of it over H bar over 4 pi C mu for H1Cl35 multiplied by R square. R is the same, H bar is a constant, 4 pi C is a constant. We are left with the reduced mass. So mu for H1Cl35 over mu for H2Cl35. Now we have the masses. So the reduced mass of the first one is mass for H1 multiplied by the mass of Cl35 divided by the mass of H1 plus mass of Cl35, all of it over mass of H2 multiplied by mass of Cl35 over mass of H2 plus mass of Cl35. We have all of these, so I will get rid of these. Just substitute them. I've done that and I have my answer. It's 0.5144. So we deduce that B bar for H2Cl35 is approximately half B bar for H1Cl35. So you can see it's approximately half its value. We have seen that the rotational spectrum of a diatomic molecule consists of a series of lines with wave numbers 2b bar, 4b bar, 6b bar, etc. So as I have said, the rotational spectrum of a diatomic molecule consists of a series of lines with wave numbers 2b bar, 4b bar, 6b bar, 8b bar, etc. So it depends on b bar. If b bar has reduced by a factor of 0.5144, then the wave numbers must also reduce by the same factor. Just multiply the above wave numbers by 0.5144 and you will get these values. So hence, we expect lines at 42.9, 53.6, 64.2 etc. سنتيمتر minus 1. يعني كل اللي عملته أنا الأرقام اللي فوق ضربتهم ب0.5144 سبب لأنه هو البي بار لل H2Cl35 بيساوي قيمته 0.5144 بي بار لل H1Cl35 فطبيعي لكن الويف نمبرز يتأثروا بنفس الفاكتور. In this exercise, we are going to derive an expression for the value of J corresponding to the most highly populated rotational energy level of a diatomic rotor at a temperature T, remembering that the degeneracy of each level is 2J plus 1. So we have seen this formula in the course. It was equal to radical KBT over 2HCB bar minus half. I'm going to derive this formula here. We said that to derive J corresponding to the most highly populated rotational energy level, we have to take the Maxwell distribution, which is function of J, and then treat J as a continuous variable, differentiate with respect to J, and then set the result equal to 0. And then find J. And this J will correspond to the J we are looking for. Will correspond to the J that has the largest number of molecules at this certain temperature. So using Boltzmann distribution, which gives the number of molecules in a certain energy level J with respect to the ground level, and J over and 0 is equal to Gj exponential minus the energy in this level over kBt, where kb is the Boltzmann constant and T is the temperature, equals the degeneracy is 2J plus 1 exponential minus the energy is equal to HCB bar Jj plus 1. This is the energy over kBt. As you can see, this distribution is a function of J. So to find the value of J for which this function is maximum, we have to derive this function with respect to J and equate the derivative equal to 0 and then find J. So let's do that. Let's do a derivative for Nj over N0. This will be equal to, so we have two parts. The first and the second, it's uv, so I have to do u prime v plus v prime u. So the derivative of the first part will be 2 exponential minus hcb bar jj plus 1 over kbt. The derivative of the second part, so we still have here 2j plus 1. I have to do a derivative for the power. So derivative of the power with respect to j, remember here we have it's a j squared plus j. So derivative for J will give us the factor minus HCB bar over KBT. So this remains, it's a constant. And the derivative for J squared plus J will be 2J plus 1. And for sure, the exponential minus HCB bar J plus 1 divided by KBT. This must be equal to 0. Let's just arrange it a little bit before. So 2 exponential minus HCB bar J plus 1 over KBT. So plus 2J plus 1 squared minus HCB bar over KBT exponential minus HCB bar J plus 1 over KBT. We have said that the derivative of the function must be equal to 0 so that the function is maximum. The number is maximum. We can take an exponential common because the exponential is never a 0. The other part or the other factor will be equal to 0. So if this is equal to 0, the exponential is not the part that's equal to 0 for sure. So we are left with 2 minus HCB bar over KBT 2J plus 1 squared equal to 0. So which is equal to 2J plus 1 squared equals to 2KBT over HCB bar implies 2J plus 1 equals radical 2KBT over HCB bar. And now J max, this is the maximum J, just arrange, it will be equal to half radical 2KBT over HCB bar minus half. You can bring the 2 inside, so it will be 4. 2 with 4, 2 is cancelled, so we are left with 2 down. So it will be radical KBT over 2HCB bar minus half. And this is the same formula shown in the explanation of the lesson. Here he asks me to find J max for a certain molecule. So evaluate the expression for ICL. He's giving me the rotational constant V bar 0.1142 centimeter minus 1 at the temperature 25 degrees Celsius. So to substitute for the temperature, we have to change it to Kelvin. We add 273 to change it to Kelvin. So let us find the J max for ICL. So for ICL, J max it's equal to, just substitute their numbers. So K is equal to 1.38 times 10 to the power minus 23. The temperature, as I have said, it's 25 plus 273. So it's 25 plus 273. It's in Kelvin like this. Divide by 2. H is 6.626 times 10 to the power minus 20 or minus 34. C is 3 times 10 to the power 8. And B bar was given 0.1142 centimeter minus 1. Change it to meter minus 1 times 10 to the power 2. So all of this is under the radical to the power half. For sure, minus half. So minus half. There's no more space. So if you calculate this, you will get approximately 29.58, which is approximately equal to 30. Because as you know, J is a quantum number, it's an integer. The closest integer to 29.58 is 30. And this is the level with the highest population for this molecule. In this exercise, we are going to derive an expression for the centrifugal distortion constant of a diatomic molecule of effective mass mu. we're going to treat the bond as an elastic spring with force constant K and equilibrium length R0 that is subjected to a centrifugal distortion to a new length R. So we're going to deal with the molecule as if the bond is elastic, and due to rotation it's going to stretch from a length R0 to a length R. Then we're going to let the particles experience a restoring force of magnitude K R minus R0 that is encountered perfectly by a centrifugal force. So there's an equilibrium between the restoring force and the centrifugal force, where omega is the angular velocity of the rotating molecule. Then introduce quantum mechanical effects by writing the angular momentum as h bar radical jj plus 1. Finally, write an expression for the energy of the rotating molecule and write an expression for dj. Let us consider, for simplicity, a single particle in rotation about a fixed point with an angular velocity omega. Assume that when there is no rotation, the particle is at a distance r0 from the fixed point, and that this length increases to a value r when the particle rotates. So just let me write that we are going to consider a single particle in rotation. A single particle of effective mass mu in rotation. During its rotation, the centrifugal force, which has a magnitude mu r omega squared, must be balanced by the restoring force, which has a magnitude k r minus r0 that accompanies bond stretching. So لما يعمل البوند stretching رح يعمل equilibrium مع centrifugal force. Balancing between the restoring force. Restoring force is similar to an elastic force. Force and centrifugal force we got kr minus r0 equals mu omega squared r. Let's arrange kr minus kr0 equals to mu omega squared r implies we get r equals, I will gather r to one side, I will get r equals to k over k minus mu omega squared r0, and at the same time we can write r0 equals k minus mu omega squared over k. Now, in difference to the pure rotation, in the approximation of the rigid rotor, where the energy of rotation is only manifested as kinetic energy, in the case of non-rigid rotor, there is a potential energy that builds up upon the change in the bond length. So لأنه نحن عم نتعاطى مع البوند كأنه شيء إلاستيك، فرح يدخل بالنون-rigid model جزء من الانرجي اللي هو potential energy in addition to the rotational energy. So the energy is now equals half I omega squared. This is pure rotation plus, similar to elastic energy, it's half kx squared, or the elongation, it's half k r minus r0 squared. Now let's change the expression of k r minus r0 squared to something similar to I omega squared. So k r minus r0 squared equals, I will substitute r0 with its value from up. It will give me k r minus mu omega squared over k r, all of it squared. It's equal to k r squared, k minus k plus mu omega squared over k, all of it squared. equals k r squared mu squared omega 4 over k squared, which is equal to r squared mu squared omega 4 over k. To create something like I omega squared, let's multiply up by r squared and down by r squared. So we will get mu squared r4 omega 4 over k r squared. Now mu r squared is I, so I square r4 is simply I square omega 4 over k r square is equal to I omega square over k r squared. So our energy, which is part rotation, part potential due to the elongation of the bond, is equal to half I omega squared. This is the classical discussion of this. So half, we replace this term by I omega squared, all of it squared, over k r squared. Now we know that the angular momentum is equal to I omega. So with the angular, because I want to replace the angular momentum by its quantized value, so the angular momentum, as he said in the question, I will write it like this. So this is the classical value of the angular momentum. It's equal to I omega. So our energy will be like this, half j squared over I plus 1 over 2 j, here we will get j4 over I squared, we still have k r squared. In quantum mechanics, so we're going now from classical mechanics to quantum mechanics. The angular momentum is quantized as, so this j, the magnitude of j, is equal to h bar radical j plus 1, where this j here is the quantum number. This j is the quantum number and this is the classical j. So equals to h over 2 pi radical j plus 1. Now implement this into the expression of energy and let's see what happens. So E will be equal to half. رح أعوض محل الJ قيمتها بالكوانتم ميكانكس ومحل الI كمان قيمتها بيطلع عندي h squared over 4 pi squared j plus 1 over mu r squared plus half h4 over 16 pi to the power 4 j squared j plus 1 squared over mu squared r4 k r squared. So this is equal to h squared over 8 pi square mu r squared j plus 1 plus h4 over 32 pi 4 mu square r6 k j square j plus 1 square. هلا اللي راح نعمله انه راح نعوض ال r بقيمتها، الاكسبريشن جبناها اول شيء in terms of r0 بأول ترم بس، بينما بالتاني ترم كرمال ما كتير نصعب الأمور لأنه هو الترم هيدا هو أصلا correction وهو كتير صغير. This is the main term, this is the rotational term and this is a correction. راح نحط ال R equal to R0, this is an approximation, but here we will substitute R for its expression in terms of R0. So I will use this expression using R equals K over K minus mu omega squared R0 in the first term only. And R is approximately equal to R0 in the second term because it's smaller. الترم كله أبو أصغر، correction أصغر. The second term. Let's see our energy appears how. So E will be equal to h squared over 8 pi squared mu. So I will substitute for R square راح يطلع عندي أكيد R0 squared K squared راح يطلع عندي هون terms اللي هن K minus mu omega squared كلها squared. I'm substituting for R squared for sure multiplied by J plus 1 and this term here remains the same over 32 by 4 mu squared R0 6 K J squared J plus. Let's expand equals h squared over 8 pi squared mu R0 squared K squared. So the first term is K squared J plus 1 and plus h squared over 8 pi squared mu R0 squared K squared. So here it's mu squared omega 4 J plus 1. I'll move to the second line. So minus h squared 2k mu omega squared over 8 pi squared mu R0 squared K squared J plus 1. And the last term is h4 over 32 by 4 mu square R0 6k multiplied by J squared J plus 1 squared. You can notice that the first term, which is the main term of the energy due to the rotational motion of the particle, depends on R0 squared, while this correction term, which is due to the stretching of the bond due to the rotation of the molecule, depends on R06. This is a small correction. So any correction that depends on R06 and higher shall be considered very, very small in comparison with these values given here. So خلينا ناخد هيدا الترم هو second term. هيدا second term, let's get rid of mu here, بيعتمد على الأوميجا 4. الأوميجا must be replaced by its quantum equivalent. أول شيء classically omega 4 is equal to the classical angular momentum divided by I4. هلا فينا نقول نحن إنه الأوميجا 4 is proportional to 1 over mu 4. Because it is multiplied by mu, so mu omega 4 will be proportional to 1 over mu cube. يعني بالآخر الميو في بقلبها R0 square مرتين، so رح يطلع عندي هيدا الفراكشن كله if I calculated في بقلبه 1 over R0 to the power 8, which is very, very small, so I can neglect this part. So all of this term will be neglected because if it is calculated, you can see that it depends on 1 over R0 to the power 8, which is higher than R06. It's considered very, very small. I'll erase these. Let's take a look on this third term. We can get rid of K here, we can get rid of mu. Okay, let's substitute the omega by its equivalent value. So h squared, we can get rid here of K over 8 pi squared mu r0 squared j plus 1. Okay, minus, let's get rid here of 2 over 4 pi squared r0 squared. We are left with k down. So omega squared shall be substituted with j squared over I squared. J squared is the classical value and its quantum mechanical value will be h squared over 4 pi squared j plus 1. So this is instead of j squared over I squared. So this is I squared here. So we have replaced omega squared with the classical j squared over I squared, and the classical j squared is replaced by its equivalent value, j plus 1. Plus the last term, which is this one, h4 over 32 by 4 mu squared r06 k j squared j plus 1, all of it squared. One more arrangement equals h squared over 8. Remember, we're trying to find the energies of a real rotor. So j plus 1. We have here minus h4. We have 4 times 4 is 16, so 16 by 4. We have I, it will be mu r0. So this is I. We will get mu squared r06, because we have r0 to the power 4 with r0 squared k, and up we will get j squared j plus 1 squared. So plus h to the power 4 over 32 by 4 mu squared r06 k j squared j plus 1 all of it squared. You can see that the second and the third term are similar, except that one has 1 over 32, the other minus 1 over 16. So we will end up with the energy equals 8 pi squared mu r0 squared j plus 1 minus h4 over 32 pi 4 mu squared r06 k j squared j plus 1 squared. So this is the energy or the quantized expression of the rotational energy in a non-rigid rotor. So now we can find the spectral term Fj. So Fj, or F of g as I used to call it, is simply the energy divided by Hc. So we will get Fg equals H over 8 pi squared mu r0 squared c j plus 1 minus h cubed over 32 pi 4 mu squared r0 6 kc j squared. So all I have done is just divided by hc plus 1 all of it squared. So this spectral term, so this is the spectral term for a non-rigid rotor, can be written this way. Fj is equal to B bar, which is the rotational constant Jj plus 1. This is the rotational constant, minus this is the distortion constant. So this is the centrifugal distortion constant, D bar, J squared J plus 1 all over squared. Let's find a relation between D and B. So first let me write D. So D is equal to H cubed over 32 by 4 mu squared R06 K times C. So B bar is equal to H over 8 pi squared mu R0 squared C. I'm going to find B cube. I'm going to reach a formula or an expression that I have given you for D, for the atomic molecule, a relation between D, B, and the vibrational wave number of the bond. H cube over 8 cube by 6 mu cube R0 6 C cube. I'll divide D by B cube. This will give me H cube over 32 by 4 mu squared R06 KC times this is 8 cube by 6 mu cube R06 C cube divided by H cube. So H is cancelled from both sides. Do a simplification. So here there remains pi squared. Here there remains mu, and for C we are left here with C squared. R0 is cancelled from both sides, and we are able to simplify this, which gives us 16. We are left with 16 pi squared mu C squared over K. If you remember from classical mechanics, if we have an oscillation or a vibration, then the angular frequency of the oscillation is equal to radical k over m. In our case, radical k over mu, because mu is the effective mass of the molecule. So omega is the angular frequency. The frequency of the oscillation will be equal to 1 over 2 pi radical k over mu. The wave number of vibration of the bond will be mu bar 1 over 2 pi, we divide by C. Okay, so radical k over mu. So this is equal to 4 over mu bar squared. So now we arrive to this relation. D bar equals 4 B bar cube divided by mu bar squared, where B is the rotational constant, D is the distortion constant or the centrifugal distortion constant, distortion constant, and mu is the vibrational wave number of the bond. Wave number of the bond. Let's move to this exercise. This exercise is an application on the previous one. It's an application on the formula that we have just derived. Estimate the centrifugal distortion constant for BR79, BR81, for which the rotational constant B is equal to 0.0809 cm minus 1, and the vibrational wave number of the bond is equal to 323.2 cm minus 1. The centrifugal distortion constant is given by D bar equals to 4 B bar cube over mu bar square. So this mu bar has nothing to do with the absorbed photon, it's just the vibrational wave number of the bond, because the bond was treated as an elastic bond. This is equal to 4 times 0.0809 centimeter minus 1 cube over, I would keep it in centimeter minus 1 because both of them are in centimeter minus 1, 323.2 centimeter minus 1 squared, so I will get my answer 2.028 times 10 to the power minus 8 centimeter minus 1. You can see that D is much smaller than B, which is always the case. The second part says, by what factor would the constant change when Br79 is replaced by Br81? In a molecule, when we replace an atom by its isotope, the bond does not change. What changes is the effective mass of the molecule. D bar depends on B and mu. Mu will not change because it is related to the bond. B will change because B is related to the effective mass. So a change in D is due to a change in B, which is in turn due to a change in the effective mass. So let's see what happens if we replace Br79 by Br81. So D bar for the molecule Br81, Br81 over D bar, so I'm going to find the ratio, Br81, this is equal to 4 B bar cube for Br81 divided by mu bar squared. We said that mu bar is not going to change, over 4 B bar cube for Br79 Br81 divided by mu bar squared. So these are cancelled, we are left with BO cube over B cube equals, I will just substitute directly for B bar, it's H bar cube over, it is 4 pi C mu, which is the effective mass of 81 BR times R squared, which is the length of the bond, all of it cube for sure, because I'm substituting B bar cube, all of it over H bar cube divided by, similarly, 4 pi C mu for 79 BR, 81 BR times R squared, all of it cube. So similarly, we will get rid of these constants. These constants are the same, R squared is the same, bond length, so we are left with mu cube for Br79 Br81 over mu cube for Br81 Br81. So in the question he gave us the masses of the atoms Br79 and Br81, they are up. So here they are. I will use them to find the reduced mass. So mu for Br79, Br81, it is the mass of Br79 multiplied by the mass of Br81 over mass of Br79 plus mass of Br81. So just substitute and you will get 39.9524 atomic mass units. So I keep it in atomic mass unit because it's a ratio and it will cancel up at the end. So mu for Br81, so it's the mass of Br times mass of Br ala mass of Br plus mass of Br. So it's the same atom in reality. It will be equal to half the mass of Br81. So just it's the same formula, but we have similar atoms here, so it will reduce to this form. Substitute, you will get 40.4581 mm. Now you have mu up, mu down, substitute, and you will get the D bar for BR81, BR81 with respect to D bar for BR79, BR81 will be equal to 0.9629. So what I have done is that I place these two values of a mu cube, divide them to get this number. So this is the relation, and this is the effect of changing an atom by its isotope on the centrifugal distortion constant. This question says, calculate in centimeter minus 1 the position of the first 4 purely rotational lines for the molecule with an internuclear distance 0.163 nanometer, and the centrifugal distortion constant d bar is given to be equal to 0.5 times 10 to the power minus 4 b bar. So he's asking us to find the wave numbers because he's asking me to find the position in centimeter minus 1 for the first 4 lines in a rotational spectrum. To find these lines, we have to start thinking about the spectral term. The spectral term depends on B bar and D bar. If we write the expression of the spectral term and then substitute J for 0, 1, 2, 3, 4, then we are able to find the difference between two consecutive levels. This difference corresponds to a line in the rotational spectrum. So the first step lies in finding B bar. When we find B bar, we are able to find D bar. Once we find B bar, D bar, we can write the expression of the spectral term Fj, and once we write Fj, we have our energy levels, we subtract them, we get our lines. To find B bar, I will start first by finding the moment of inertia of the molecule. So I is equal to mu r squared, where mu is the reduced mass. It's equal to the mass of Cl multiplied by the mass of F divided by the mass of Cl plus mass of F r squared. Mass of Cl is 35, mass of F is 19 over 35 plus 19. If I'm going to consider this in gram per mole, so I have to multiply by 10 to the power minus 3 to make it in kilogram, and then divide by Avogadro's number, 6.022 times 10 to the power 23, multiplied by r squared, 0.163 times 10 to the power minus 9 squared. This is equal to 5.433 times 10 to the power minus 46 kilogram meter square. Now let's calculate the rotational constant V bar. V bar is equal to h over 8 pi squared Ci. It's equal to 6.626 times 10 to the power minus 34 divided by 8 pi squared, 3 times 10 to the power 8, and I is 5.433 times 10 to the power minus 46. Everything is in SI units, so we will get our V bar in meter minus 1, and the answer is 51.487 meter minus 1. To change it to centimeter minus 1, so it's equal to 51.487 times 10 to the power minus 2 centimeter minus 1. So we get 0.51487 centimeter minus 1. Now after finding B bar, we are able now to find D bar. He gave us a relation between D bar and B bar. So, sorry, here this must be, this should be 1.70 and this here must be minus 6. So now let's find d bar. D bar is equal to 1.703 times 10 to the power minus 6. B bar is equal to 1.703 times 10 to the power minus 6 multiplied by 0.51487 centimeter minus 1. So we get our answer 8.77 times 10 to the power minus 7 centimeter minus 1. Now having found D and B, we are able to write the spectral term F. So F of J gives us the wave numbers of energy levels in centimeter minus 1. Once we subtract the difference between these energy levels, you are able to find the wave numbers of the absorbed radiation. So the formula says Fj equals B bar J plus 1 minus D bar J squared J plus 1 squared. I'm going to calculate the energy of at the levels 0, 1, 2, 3 till 4 because we are going to find the first 4 lines. I'll draw a table showing the spectral term for different values of J. So this is my table. 1, 2, 3, 4. We have J, we have F bar J, and the energy in centimeter minus 1. First, if J is 0, then F bar is 0 and the energy will be 0. If J is 1, then we get 2B bar minus 4D bar. Substitute, we have B bar, we have D bar, we will get 1.029 minus 3.5 times 10 to the power minus 6. You can see that, which is approximately equal to 1.029. You can see that the correction is very, very small. This distortion correction in the case of this molecule is really, really very small. Now for J equals 2, we get 6B bar minus 36D bar. So it will be 3.089 minus 3.157 times 10 to the power minus 5, which is also approximately equal to 3.089. The correction is also small. So for 3, we have 12B bar minus 144 D bar. It's 6.178 minus 1.26 times 10 to the power minus 4, which is approximately equal to 6.178. So you can see that the correction is not important or it's negligible in this case. So for the last J I'm searching for, so this is for 20 B bar minus 400 D bar. It's 10.29 minus 3.51 times 10 to the power minus 4, which is also approximate to 10.29. Let's find the wave numbers of the absorbed radiation or the absorbed photons. You know that in the case of absorption, there is a transition from a level J to J plus 1. So, let me do a table. So, from J to J plus 1, and we're going to calculate the energy of the photon. So, energy of absorption in centimeter minus 1. So from 0 to 1, all we have to do is just subtract the energies. It's from the upper table. Let me go up. So you can see that it's 1.029 minus 0 is equal to 1.029 29 centimeter minus 1. And this is the wave number of the first line. Now from 1 to 2, we subtract 3.089 minus 1.029, and we will get 2.06 centimeter minus 1. From 2 to 3, we subtract 6.178 minus 3.089, and we will get 3.09 centimeter minus 1. And the last one, it's 3 from 4, it's equal to 10.29 minus 6.178, and we will get 4.112 centimeter minus 1. And you can see that we have found 4 energies of 4 lines in the absorption spectrum of this molecule. Let's move to this exercise. I will solve this exercise rapidly, similar to previous exercises. I will allow you to solve it at home on your own and give you the answers. The last part of it is a little bit new. So the HF molecule has rotation lines separated by 41.9 cm minus 1. Calculate its moment of inertia, the length of the bond, and its angular velocity in the first 4 levels of rotation. So we know how to find I, we know how to find R. Let's see how to find the angular velocities for the first 4 levels of rotation. First, I'll remind you how to find I and R rapidly. So he said that the rotational lines are separated by 41.9 cm minus 1. And we all know that the separation between the lines is equal to 2 b bar. So simply, b bar will be equal to half this value, 41.9 cm minus 1, which will give us 20.95 centimeter minus 1. Now we have found b bar, we are able to find I. So remember that b bar is equal to h over 8 pi squared ci, implies I is equal to h over 8 pi squared c b bar. You have everything, put everything in SI units, and you will end up with 1.335 times 10 to the power minus 47 kilogram meter squared. So this is the moment of inertia. Now we are looking for the bond length. To find the bond length, let's find first mu, because I is equal to mu r squared, so we have to find first mu, the reduced mass. And mu is equal to the mass of H, mass of F, divided by mass of H plus mass of F. In your calculations, you will get 1.577 times 10 to the power minus 27 kilogram. So once finding mu, now we are able to find R. Simply I is equal to mu r squared, so implies R is equal to radical I over mu. We have found I, we have found mu. Now dividing these will give us 9.19 times 10 to the power minus 11 meter, which is equal to 0.0919 nanometer. So this is the radius. In the last part, we have to find the angular velocity in the first 4 levels of rotation. We have to find omega. Omega 0, omega 1, omega 2, and omega 3. To find omega, we know that the angular momentum J is equal to I omega. Omega is a classical symbol for rotation, while J carries a quantum mechanical meaning. We know that J classically is equal to I omega. And J quantum mechanically has a magnitude of h over 2 pi radical j plus 1. Okay, so we can say that quantum mechanically omega, if we're going to find omega, for the levels that we have which are quantized, omega is equal to h over 2 pi I. يعني هي simply j على I، والj هي امتى quantum mechanically بهالطريقة radical j plus 1. So all we have to do now is substitute for J0, J1, J2, and J3, because he needs the force the first four levels. So I have already calculated this constant. So h over 2 pi I, it's equal to 7.899 times 10 to the power 12 radical j plus 1. So all we have to do is just multiply by the values of j. So this is a table for j0 omega, for sure omega in radians per second or in seconds minus 1. For j0, omega is 0. For j1, we multiply by radical 2, we get 1.11 times 10 to the power 13. For j equals 2, we multiply by radical 6, we get 1.93 times 10 to the power 13. For j equals 3, this is the last one, we multiply by the 3 plus 3 is 4, 4 times 3 is 12. We multiply by radical 12 and we get 2.73 times 10 to the power 13. And these are the angular velocities of rotation in these four energy levels. Let's check this exercise. The distance NO in the nitric oxide molecule is 0.115 nanometer. By the way, nitrogen has a mass number 14 and oxygen has a mass number 16. Calculate its moment of inertia. So I will leave the calculation for you. I is equal to mu r squared. Mu is the mass of nitrogen multiplied by the mass of oxygen over the mass of nitrogen plus the mass of oxygen, and you have r squared, you have everything. Just substitute, you will get your answer 1.64 times 10 to the power minus 46 kilogram meter square, and this is the moment of inertia. So in part B, calculate the energy for rotational levels J equals 1, 2, 3, 4. We have to calculate these energies. We know that the energy of the level J is equal to HCF bar of J is equal to HCB bar J plus 1. It's equal to HC. B bar we can substitute it with its value. It's H over 8 pi squared Ci J plus 1. So all of these are similar. Ej is equal to H squared over 8 pi squared. C is cancelled, so we are left with I J plus 1. I have calculated this constant. So this constant was found to be 3.39 times 10 to the power minus 23 J plus 1. So to find the energies now, all you have to do is just substitute J. J1, J2, J3. I'm going to do a table and check the answers yourselves. So this is the table. G for J, energy of J in joule. So for 1, I found the answer to be 6.78 times 10 to the power minus 23. For 2, I found it 20.34 times 10 to the power minus 23. For 3, I found it 40.68 times 10 to the power minus 23. And for level 4, it was found to be 67.8 times 10 to the power minus 23. Now let's move to the second part, part C. In C, calculate in wave number the frequency of the absorption line when J passes from 0 to 1, 1 to 2, 2 to 3. So we have to calculate the wave number of absorption lines, wave numbers of absorption lines. So to calculate the wave numbers, in reality we have two methods. We can depend on part B to calculate them, or we can just use the formula for the absorption spectra. Let me talk about both of them. So first, what I can do is that, this is part C, to calculate the wave number of an absorption from J to J plus 1, all I have to do is find the difference of energy levels delta E from J to J plus 1 and divide this difference by Hc. It's the energy of J plus 1 minus the energy of J and divided by Hc. For example, to find the wave number for a transition from 0 to 1 بروح بنقص الانرجي للليفل 1 من الانرجي للليفل 0 وبقسم على Hc easily. Or we can do this. U bar for a transition from J to J plus 1 is equal to the spectral term F bar J plus 1 minus Fj, as we have seen that in the course. This is equal to 2 B bar J plus 1. You can calculate B bar aside, you have everything. So this is J. I'm going to substitute B bar here, so it's 2H over 8 pi squared Ci J plus 1. So I have already calculated this constant, which is multiplied by J plus 1. It was found to be 341.13. So its unit for sure is meter minus 1 because everything was substituted in SI unit, J plus 1. I prefer it to be in centimeter minus 1, so I will write it as 3.41, enough decimals. So J plus 1, and this is expressed in centimeter minus 1. So this is the answer in centimeter minus 1. Now to find the wave numbers of transitions from 1 to 2, for example, you have to do 3.41 multiplied by 2, which is equal to, did he ask for a transition from 0 to 1? Okay, so he asked for a transition from 0 to 1. Let me start from 0 to 1. So I have to substitute for the smaller j, it's 1, and the answer is 3.41 centimeter minus 1. For a transition from 1 to 2, it's same constant multiplied by j plus 1. 1 plus 1 is 2, so the answer will be 6.82 centimeter minus 1. And the transition from 2 to 3, it's equal to 3.41 multiplied by 3, which is equal to 10.23 centimeter minus 1. Now last part, D. So D says if half kT is the available energy per degree of freedom of rotation, compare this energy to the energy required for the transition from J equals 3 to J equals 4. بالنسبة للموليكول اللي هي diatomic molecule عندها بالحقيقة 2 degrees of freedom of rotation، لأنه هي بحق لها تعمل rotation ب 2 perpendicular planes. هي ما بحق لها تعمل rotation around the internuclear distance، كرمال هيك ما عندها 3 degrees of freedom of rotation، عندها بس 2. فلكن إذا عندها 2 يعني هي ال energy available for it will be kT. K is the Boltzmann constant. So let's calculate this energy available for the molecule due to the temperature. So now we're in part D. KBT is equal to 1.38 times 10 to the power minus 23 joule per Kelvin. I have to substitute T in Kelvin. At ambient temperature at 25 degrees Celsius, it's 298 Kelvin. It's equal to 4.11 times 10 to the power minus 21 joule. So for a transition, the energy needed for a transition from J equals 3 to J equals 4 is simply E4 minus, so energy for a transition simply E4 minus E3. E4 and E3 are calculated up. You can see them. This one is 67.8 times 10 to the power minus 23 minus 40.68 times 10 to the power minus 23. So the answer is 2.712 times 10 to the power minus 22 joule. If we divide E of transition, or the energy needed for the transition, by kBT, just to get an idea, this fraction or this ratio will be 0.065. So you can see how much the energy difference between these levels is small, incomparable with kBT. So the temperature, or at ambient temperature, there is enough energy for the molecule to go from the level 3 to the level J. So the energy delivered by this temperature is enough. So this is equal to 6.5%. And this is the conclusion. Let's move to this exercise. The wave number of the incident radiation in a Raman spectrometer is 20,623 centimeter minus 1. So he's giving me the wave number of the incident photon. What is the wave number of the scattered Stokes radiation for a transition from J equals 2 to J equals 4 for O2 molecule if B bar equals 1.4457 centimeter minus 1? So all I have to do is just apply the formula. Let me remind you, the wave number of a Stokes line in rotational Raman is, so the wave number for Stokes, it's equal to mu I bar minus 2b bar 2j plus 3. We have derived this formula in the course, where j is the initial rotational state. Initial rotational state. So if we have a transition from 2 to 4, we substitute for J2, rotational state. So in our case, mu bar is equal to 20,623 centimeter minus 1 minus 2, B bar is 1.4457 centimeter minus 1, same unit, and 2 substitutes for J2 plus 3, and this is equal to 20,603 centimeter minus 1. You can see that the wave number is smaller than the incident wave number. So this is the case for Stokes lines. The rotational Raman spectrum of F2, the mass of F is given, shows a series of Stokes lines separated by 3.5312 cm minus 1 and a similar series of anti-Stokes lines. So this is the separation between Stokes lines and anti-Stokes lines. Calculate the bond length of the molecule. This is easy. We know that the separation in the case of Stokes and anti-Stokes lines is 4 B bar. So we are able to calculate B bar. Once we calculate B bar, we can find I. Once we find I, we are able to find R. So it's similar to previous questions. I'm just going to write it rapidly. So the separation of lines is 4B bar. So B bar will be equal to 1 over 4, the number given up, 2 centimeter minus 1, and the answer is 0.88280 centimeter minus 1. Now to calculate R, we all know that B bar is equal to H over 8 pi square C I is equal to 8. I will do it directly. 8 pi square C mu R square, we are searching for R, implies R is equal to H over 8 pi squared C mu B bar, all of it under the radical, so it's half, and mu is equal to multiplication of the masses over the sum of the masses, and because the masses are equal, it's equal to half the mass of F. And we arrive to H over 4 pi square C, the mass like F, times B bar half. معكم ال H معكم ال C معكم الماس لل F. الماس لل F is in atomic mass unit, change it to kilogram. معنا ال B bar, change it to meter, and you will get your answer 1.417 times 10 to the power minus 10 meter, which is equal to 141.7 picometer.